In the world of medicine, advancements are made every day to help improve the lives of billions across the world. But have you ever wondered what the most instrumental medical advancement of all time is? Is it vaccines? Antibiotics, maybe? While both of these things have been instrumental in shaping the medical field, there's one other discovery that's had a revolutionary impact in diagnosing and solving some of the most prolific medical problems. Of course, I'm talking about monoclonal antibodies. Monoclonal antibodies, or MABs for short, are a type of protein that plays a crucial role in our immune system. They're highly specific, meaning they only bind to a specific molecule known as an antigen. This is often a protein on the surface of a cell. Being able to bind in such a sophisticated manner makes them invaluable in medicine and research. Now, in general, antibodies are actually produced by our bodies all the time. They're a Y-shaped protein with three distinct parts: the heavy chain, the light chain, and the antigen binding region. These are specifically designed to target and neutralize pathogens such as bacteria and viruses. When such pathogen enters our body, it triggers a complex immune response. A key cell in this response is the B cell, a type of white blood cell. B cells are what produce antibodies. When a B cell encounters a pathogen, it recognizes and binds to specific antigens on the pathogen's surface. This binding activates the B cell, causing it to divide and differentiate into plasma cells. Plasma cells are highly specialized cells that produce large quantities of antibodies. The antibodies produced by these plasma cells circulate through the bloodstream, seeking out and binding to the same antigen on other pathogens. While our immune system can produce a variety of antibodies, they're often a mix of different types that target various antigens and referred to as polyclonal. This can make it difficult to isolate and study a specific antibody. That's where monoclonal antibodies come in. The process of creating monoclonal antibodies involves several key steps. Step 1. Immunization. Step 1. An animal, often a mouse, is injected with the antigen of interest. This triggers the animal's immune system to produce antibodies against the antigen. Step 2. Cell fusion. B cells from the immunized animal are isolated and fused with immortal myeloma cells. This creates hybrid cells called hybridomas. Step 3 is selection. The hybridomas are screened to identify those that produce the desired antibody. This is often done using a technique called ELISA, which can detect the presence of specific antibodies. Step 4. Cloning. The selected hybridomas are cloned to create a population of identical cells that produce the same antibody. Finally, Step 5. Production. The cloned hybridomas can be grown in culture or injected into animals to produce large quantities of monoclonal antibody. This method of synthesizing monoclonal antibodies has revolutionized medicine. Because of it, we can treat a wide range of diseases, including cancer, autoimmune disorders, and even organ transplantation. Let's have a look at how monoclonal antibodies are used in a bit more detail. Transplantation is the process of taking an organ or tissue from one source and implanting it into another. This makes it possible for individuals suffering from organ failure to have a chance at survival. One of the biggest challenges in transplantation is rejection. The recipient's immune system often recognizes the transplanted organ as foreign and behaves in a way similar to the Yakuza seeing someone they don't know donning a dragon tattoo. But why? Well, there are markers in our cells and they're called MHC or HLA. Everybody has unique HLA markers, and these help tell our immune systems that a cell is friendly. However, since the transplanted organ comes from a different person, the HLA is different, thus, the immune system actually recognizes it as foreign and launches an attack. This leads to rejection. Monoclonal antibodies can be used to prevent rejection by targeting molecules like HLA that are involved in the process of activating and recruiting immune cells. By blocking these molecules, monoclonal antibodies can prevent immune cells from attacking the transplanted organ, thus preventing rejection. There are a number of different antibodies that are used in transplantation. Let's go through some of the most common examples. CD4 T cells, or helper T cells, are the immune cell which activates most of the other cells during an immune response. CD4 is a protein on the surface of these cells that recognizes HLA markers on other cells. Anti-CD4 monoclonal antibodies can target and neutralize these cells so that no immune response takes place. AT2 is a MAB that targets the CD3 molecule on T cells. Remember that T cells are the immune cells that usually start an adaptive immune response. CD3 is an activator and will help the T cell initiate an immune response. By blocking CD3, AT2 can suppress T cell activation, thus preventing rejection.
Finally, ICAM1 is a molecule involved in cell-to-cell communication and activates helper T cells to recruit other leukocytes to the site of infection. By blocking ICAM1 with anti-ICAM MABs, researchers have found that they can improve the chances of organ acceptance.
It's important to note that MEBs used here are immunosuppressive. They shut off your immune system, and the patients that do undergo transplantation in general have to live with these drugs for life. With continued research, we may be able to achieve long-term tolerance, where the recipient's immune system accepts their transplanted organ as if it were their own. Cancer is a disease that occurs when cells in the body grow and divide uncontrollably. These abnormal cells can form a mass or tumor, which can spread to other parts of the body. Cancer cells are extremely good at avoiding immune cells. This is because they're actually self cells and display self-HLA. This is a problem because these cells start usurping nutrients from all the cells around them, causing adverse effects. There's many different types of cancer, each with its own unique characteristics and treatment options. In majority of these treatments, doctors will use MABs to target cancer cells and activate the immune system. Let's see how this can happen. The antibody Herceptin binds to a protein called HER2, which is overexpressed in some types of breast cancer. Herceptin can block the growth and spread of HER2-positive breast cancers by directly interfering with HER2 signaling. The MAB Rituxan, which targets a protein called CD20 on B cells, can activate the immune system to destroy cancer cells. Rituxan is used to treat non-Hodgkin's lymphoma and chronic lymphocytic leukemia. The antibody Avastin can be linked to chemotherapy drugs, allowing these drugs to be delivered directly to cancer cells. Avastin is used to treat a variety of cancers, including colorectal cancer and lung cancer. By targeting VEGF, a protein involved in the formation of new blood vessels, Avastin can also prevent cancer cells from receiving nutrients and oxygen they need to grow and spread. Monoclonal antibodies have revolutionized how physicians can eliminate cancer in a non-invasive way. Note that the antibodies used here are made to enhance the immune cell's vision on the sneaky cancer cells. They help make detection and destruction of cancer a cakewalk. Autoimmunity is a condition where the body's immune system mistakenly attacks its own healthy cells. This can lead to a variety of diseases, as the immune system's intended function is to protect the body from foreign invaders. When the immune system becomes confused and starts attacking itself, it can cause inflammation, tissue damage, and another range of symptoms. Some examples of autoimmune diseases include rheumatoid arthritis, which is an inflammation of the joints, type 1 diabetes, the destruction of insulin-producing cells in the pancreas, hay fever, an allergic reaction to pollen, and psoriasis, a skin condition characterized by patches of red, scaly skin. MABs can be used to treat a variety of autoimmune diseases. These MABs work in several ways. They can neutralize by binding to harmful molecules and stop them from causing damage. They can adjust the immune response by acting or suppressing specific immune cells. They can also help deliver other drugs like radioactive isotopes directly to target cells. Let's take a look at what some MABs do to combat autoimmunity. MABs like infliximab target TNF-alpha, a signaling molecule that triggers inflammation. By stopping inflammation from occurring, they help improve the joint pain that's characterized by rheumatoid arthritis. MABs such as etanercept target TNF-alpha or IL-17. This helps reduce inflammation that causes skin lesions, providing relief to patients suffering from psoriasis. Though not yet available to consumers, research is ongoing to try and stop B cells from producing autoreactive antibodies that target pancreatic cells that produce insulin. This would greatly improve the quality of life for people suffering from type 1 diabetes. So now you know just how versatile monoclonal antibodies are, and hopefully you appreciate just how impactful this discovery was to the world of medicine. The possibility for future research is endless, and as our knowledge improves, so will our applications for these antibodies. Hopefully you learned something, and we'll see you again soon.